Every algorithm produces a performance profile dictated by its internal logic. This execution speed is a mathematical derivation based on how loops and recursor calls handle data. Take bubble sort. It uses two nested loops to push the largest elements to the end of a list. Looking closely at those loops reveals a predictable mathematical series. In the first pass, the algorithm compares every adjacent pair of elements. By the end of that pass, the largest number is locked into place. For the second pass, the searchable area of the array has shrunk by exactly one element. If we start with n elements, the first pass takes n-1 comparisons. The next takes n-2. This continues until only a single comparison remains. We are left with a cumulative addition problem, n-1 plus n-2, all the way down to 1. This is a standard arithmetic progression. The sum of the first n-1 integers simplifies to n times n-1 divided by 2. When n represents millions of elements, the n-squared term dictates the growth rate. Dropping the constants and lower order terms leaves a time complexity of big O of n squared. Establishing this n-squared baseline provides a concrete standard. It allows us to measure whether an alternative approach actually optimizes the process or merely repeats the same workload. Divide and conquer algorithms attempt to beat that baseline, but quicksort's efficiency relies on its partition phase, specifically the choice of the pivot element. In a reversely sorted array, choosing the last element as pivot fails to divide the data, isolating one element. Instead of dividing work, we subtract. Time for n equals time for n-1 plus linear partition time, resolving to big O of n squared. If the pivot is the median value, it perfectly halves the array, building a balanced binary tree. One problem of size n becomes two subproblems of size n over 2, plus linear partition time. This solves to big O of n log n. This pivot dependency reveals a critical vulnerability. Without a balanced split, the divide and conquer strategy fails, causing the algorithm to exhibit the same quadratic growth as a basic nested loop. Heap sort provides a mathematical guarantee of n log n speed, regardless of the input data, eliminating the instability seen in quicksort. The first phase organizes the initial data into a max heap tree structure. Working from the bottom nodes up to the root, this build phase requires linear time, or big O of n. During the sort phase, the algorithm swaps the root to the end and sifts down the new root. A tree with n elements has a height of log n. Repeating this for all n elements results in an n times log n calculation. Because this process is mapped directly over the existing array, no extra memory is needed. Heap sort achieves guaranteed n log n execution time within a constant big O of 1 space footprint. We can apply this logic to matrix multiplication. Before looking at advanced optimizations, we must establish the baseline for a standard divide and conquer approach. Splitting two n by n matrices into smaller blocks requires 8 sub-multiplications, each half the size of the original. This produces a specific recurrence relation. Using the Master Theorem, identify the values for A, the number of subproblems, and B, the division factor. Review the 3 cases to determine which complexity class applies. With A at 8 and B at 2, n to the power of log base 2 of 8 equals n cubed. The leaf nodes dominate the work, resulting in big O of n cubed. For large matrices, this becomes a significant computational bottleneck. Strassen's algorithm bypasses that bottleneck. Using algebraic additions and subtractions, he reduced the number of recursive multiplications from 8 down to 7. This adjustment changes the core variables of the recurrence relation. The A value is now 7. Recalculating with these variables gives n to the power of log base 2 of 7, producing a fractional exponent. Log base 2 of 7 is approximately 2.81. This result proves algebra can lower an algorithm's growth rate below standard limits. This matrix tracks our findings, from simple loops to algebraic optimizations. Analyzing the growth of these equations allows you to anticipate how an algorithm will behave at scale.